If we don't have more questions, we can switch to the second speaker, which is
Okay.
Albert Lee.
Thank you.
Thank you.
And let me introduce Albert first. Albert is a PhD candidate at the Center for Innovative Structures and Materials at RMIT University. After completing his Bachelor of Arts degree at Tianjin University in 2018, he embarked on the PhD program in civil engineering in 2020. Albert's active research area includes structural optimization, computational design, discrete geometry processing, and digital fabrication. Let's welcome Albert for his topic, interactive structural topology optimization with subjective scrolling and drawing systems.
Okay, thank you for everyone. Welcome to join this presentation. I'm Albert Lee. I'm glad to share my recent research in interactive structural topology optimization with subjective scoring and drawing systems, which was supervised by distinguished Professor Mike Xie, Dr. Jeff Lee, and Professor Roland Snooks. The outline of this presentation includes 6 parts. Firstly, I'm going to introduce the background of this research. Secondly, the proposed SP-BESO method will be illustrated. Thirdly, I will show the released digital design tool, iBESO, which is developed based on the SP-BESO method, followed by parametric investigations and practical applications will be introduced, and a conclusion to summarize all findings. Topology optimization is a generative design technique that can create lightweight and high-performance structures by distributing materials in design domain. Conventional topology optimization methods rely on finite element analysis. This technique can calculate the local structure performance of discrete elements, as shown on the screen. Based on the quantified values, topology optimization can iteratively explore the most efficient structure form according to the input design domain, loading and boundary conditions, and volume constraint. Among many topology optimization methods, a widely used technique is the bi-directional structure optimization method, so-called the BESO method, which is proposed by Professor Mike Xie and Professor Xiaodong Huang. This technique can add and remove finite elements simultaneously to improve material distribution. In recent years, this technique has been used in various structural designs, including bridges, furniture, and architectural design, as shown on the screen. However, existing topology optimization techniques are purely based on structure performance, which means that the results cannot always satisfy all design requirements, such as personalities, fabrication costs, and aesthetics. To overcome this bottleneck, recent research has developed multi-solution strategies based on the BESO method. Such approaches sacrifice a small amount of structural performance in exchange for diverse design options. The obtained solutions have different shapes while maintaining a high level of structural efficiency. The existing strategies can be achieved by introducing randomness to disturb the optimization process, changing the optimization settings, and adding structural complexity control. However, although multi-solution strategies can provide many design options, finding the desired design is a difficult task. One reason is that evaluating each design option is time-consuming. Another reason is that real solutions can satisfy design requirements according to differences in personality. Therefore, too many design options can lead to a high cost in selecting a satisfying design. This is called the overchoice problem. So, what is a good design process? The design exploration is an evolutionary process rather than choosing an appropriate outcome from various options. Designers should add their subjective considerations to guide the design process. As a result, the optimization process should allow more subjective involvement. It should be noticed that different design tasks require different levels of subjective involvement, where low and high levels of involvement can result in performance-driven and preferences-driven design, respectively. Performance-driven design don't need too much subjective involvement. Hence, they are suitable for applications where structural performance is important, such as bridge design and mechanic design. Although such designs can create high-performance configurations, designers typically fail to add their creative ideas to affect the final outcomes, meaning designers have to passively accept the optimal solution. On the other hand, preferences-driven design focus on creativity and aesthetics, and they are less concerned about objective performance. Thus, the key geometric feature of the final design can be fully controlled by subjective preferences like furniture design and jewelry design. So the optimization process is utilized as a supporting role in design exploration. However, few studies have focused on topology optimization based on subjective preferences, which is an ongoing challenge and remains underexplored. To solve the above issue, our research proposed a new topology optimization method considering subjective preferences, named SP-BESO. It is based on the BESO method. Let's look at how this method works. The stiffness maximization problem subjected to a volume constraint can be formulated as shown on the screen. Among many steps in the BESO framework, an important part is sensitivity analysis, which can rank the elements according to the results of finite element analysis. The ranked elements can be optimized using the bisection method to create the optimal design. In other words, the sensitivity field represents the consideration of structural performance and decides the formation of a final design. So, if we visualize the elemental sensitivity field with a texture, we can obtain a grayscale image, which will be useful in the following steps. To generate multiple solutions, this study introduced the random perturbation method proposed by Yunzhen He. In their method, the sensitivity number alpha is penalized by a random coefficient beta, which affects the selection of elements being added or removed. Moreover, the generation of random coefficients is driven by the random seed integer gamma, where different gamma can result in different sets of random coefficients. Due to this, infinite solutions can be obtained by modifying gamma, thereby significantly improving the design diversity of topology optimization. If we also visualize the random perturbation field with a texture, the multi-solution method can be understood to multiply these two fields during sensitivity analysis. Next, let's introduce subjective preferences. This study proposed a simple approach to quantify subjective preferences by scoring the existing solutions. The subjective scores are used as weights in topology optimization to generate new designs. To clearly introduce the proposed method, we call the existing design to parent design, and the subsequent new designs are child designs. The scoring weight, omega s, is used to penalize the elemental sensitivity number. The modified sensitivity number alpha s can be calculated by the equation shown on the screen. S is the subjective score. When S is smaller than 0, the parent design is considered an undesired solution. When S is larger than 0, the parent design becomes a preferred solution. Lambda s is a scoring parameter ranging from 0 to 1, which allows users to control the influence of scoring weights on topology optimization. Another strategy to consider subjective preferences is using hand-drawn patterns. drawings allow designers to show their creative ideas. However, it is difficult for designers who lack structural design experience to produce high-performance sketches. Due to this, we convert the given drawing pattern into drawing weights to modify the elemental sensitivity number. In doing so, these numbers can guide the optimization process to achieve a satisfying designs. In detail, a drawing pattern is first translated to a grayscale texture made up of pixels. The colors of pixel are used to calculate the drawing weight omega d. Then, the modified sensitivity number alpha d can be calculated by the equations shown on the screen. Note that controlling the two parameters lambda e and lambda d allow users to balance objective structural performance with subjective preferences according to design requirements. Finally, a new design integrated with the drawing pattern is created. Also, the drawing system can be based on the existing solution. First, the nodal sensitivity field of the existing design can be converted to a texture. Using the bilinear interpolation method. Next, users can draw or remove some structural members from the texture. The texture is then used to calculate the drawing weights for the subsequent topology optimization. Finally, a new design is created based on the updated drawing weights. Now, let's sum up all techniques together. The SP-BESO method is proposed based on the combination of the multi-solution strategy, subjective scoring, and drawing systems. The integrated sensitivity number used in the SP-BESO is shown on the screen. From the field perspective, the updated sensitivity field equals the random perturbation field times the scoring field times the addition of the raw sensitivity field and the drawing field. The computational workflow of the proposed method is summarized in the flowchart shown on the right. The new features are highlighted. As can be seen that by alternately inputting subjective preferences and executing topology optimization, users can iteratively explore the desired design. In this way, a human-centered design exploration is created. To further explore the capability of the proposed SP-BESO method, a user-friendly digital design tool, iBESO, is developed. It has three unique systems: the multi-solution system, the scoring system, and the drawing system. The implementation of iBESO is achieved by using both C++ and C# programming languages. The C++ part contributes an efficient optimization kernel, which is modified based on existing optimization code. The C# part gives the graphical user interface, allowing users to change parameters and define boundary conditions interactively. The iBESO software can run 4 SP-BESO solvers simultaneously. This allows 4 parent designs to be parallel evaluated and further modified based on subjective preferences, resulting in child designs through subsequent topology optimization. The evaluation and modification process can be repeated until an ideal structural design is obtained. Next, I will show the features of iBESO through a video. Okay, thank you for watching. In this study, we conducted two sets of parametric investigations using the iBESO software. To compare two given structural topologies, three metrics are used to quantify the differences in shape and structure performance. Firstly, the difference in structural performance can be represented by the compliance ratio, delta C. Secondly, the overlapping rate P can be used to measure the similarity of the two solutions. The calculation of the overlapping rate is shown on the screen. For example, the blue design is solution A and the green design is solution B. Their overlapping part is the yellow area shown on the screen. We can find the overlapping rate is 89%. Note that the overlapping rate alone is inefficient to show the geometric difference. Hence, the third metric, delta G, is used to measure the difference in the number of holes. Mathematically, the number of holes in a solution can be calculated based on the geometric information of the obtained mesh model. For example, solution A has 3 holes, solution B has 5 holes. The delta G equals GB minus JA equals 2. In the following study, solution A and solution B are considered highly similar, then delta C approximates 1, P approximates 1, and delta G approximates 0. Let's look at a classic 2D short cantilever example. The optimization settings are shown on the screen. In the parametric investigations, we regard the original BESO result as the parent design. Then we test the influence of scoring weights on optimization results by changing the subjective score S and the scoring parameter lambda S. All the tests are based on the same parent design with lambda S equals to 0.1, 0.5, and 1, and S equals to -3, -1, 1, and 3. Therefore, 12 child designs are created. They are then compared with their parent design using the proposed metrics. To avoid interference with the drawing system, lambda D and lambda E are set to 0 and 1 respectively. The results of testing the scoring weights are shown on the screen. Firstly, it can be seen that the solution A and B with deselect scores have different shapes. All the overlapping rate P are less than 90%, and the lowest case has almost 50%. When lambda S increases, P becomes smaller. Besides, most delta G are not zero, meaning the child designs are different from their parent. Together, this results indicates that the disliked score can result in diverse solutions. In contrast, solutions C and D have preferred scores, so their shapes are similar to the parent design. As shown on the screen, as can be seen that their P are relatively high, ranging from 89% to 98%, and the delta G is either 0 or -2. Moreover, either high or low lambda S can make the child design close to the parent design because they have already been the preferred solutions. It indicated that the preferred score can result in similar designs to the parent design. In terms of structural performance, there is just a little difference between these 12 solutions. The maximum performance loss is 3.8%. Other designs have performance variations within 2%. The evaluation history figures are shown on the right. Together, it can be concluded that both lambda S and S can control the formation of final topologies. In the following investigations, we test the influence of drawing widths using 5 child designs. The drawing pattern is a creative sketch as shown on the screen. The 5 child designs are created using different combinations of lambda d and lambda e, which can be further represented by delta lambda. The parameter settings are listed on the screen. Then the child designs are compared with 2 reference designs. Reference 1 is the original BESO result. Reference 2 is the drawing pattern redesigned using topology optimization to achieve the target volume. The 5 child designs obtained using different combinations are shown on the screen. If we set a low delta lambda, the child design will tend to be similar to reference 1. But if we set a high delta lambda, the child designs tend to be similar to reference 2. This indicated that delta lambda plays an important role in determining whether the child designs are performance-driven or preferences-driven. This statement is supported by their compliance values and similarities. The bottom left graph shows the evolutionary history of child designs. The bottom right figure shows the overlapping rate of the child designs compared with the 2 references. It can be concluded that although performance loss may be unavoided using drawing widths, the child design has the potential to meet multiple design requirements and inspire designers. In addition, we use 2 examples to demonstrate the potential of the proposed method in practical applications. The first example is a simple 2D bridge. As shown on the screen, the size of a bridge is designed to be 240 mm wide and 80 mm tall. Due to symmetry, only half of the structure needs to be modeled. The loading and boundary conditions of the bridge are shown on the screen. The design target is to achieve many holes in the structure topology as possible. It is also desirable to obtain a final design that is performance-driven but includes subjective considerations. After running iBESO, the first 4 parent designs are obtained by purely performance-driven settings. As can be seen that solution A and B have more holes. Hence, they are considered preferred candidates to create the next generation. The 4 new solutions are created using the scoring system. The scores are 4, 4, -4, and 4, -1 respectively. Interestingly, all child designs have 11 holes, and their performance loss is within 4%. Comparing these solutions, their whole arrangements are different. Where A to C are arranged as 3, 5, 3, but solution D has 8 holes at the bottom of the bridge. Thus, we pick it as the preferred design and use the drawing system to improve it further. Then, a manually drawn pattern is used to create a new generation of child designs. All solutions have a highly similar shape with 13 holes and structure performance. Here, solution A is selected as the final design because it has the best performance. The second example is a 2D chair, which is a preferences-driven task. The design domain is designed to be 80 mm deep and 80 mm tall. The seat and the backrest part are set as a continuous passively solid domain, subjected to a uniform load of 1 Newton per millimeter. 2 points are fixed at the bottom of the design domain. The design target is set to maintain subjective ideas while improving structure performance. Reference 1 shown on the screen is a purely BESO result, and reference 2 is a curved chair design inspired by Frank Gehry's. It is created by using purely preferences-driven design settings. The figure shown below is the first generation is obtained by lambda e equals 1 and lambda d equals 0.5, aiming to achieve improved structural performance with a small distortion of the drawing pattern. As can be seen that all child designs have successfully preserved the drawing pattern with additional members, which enhance the structural performance. Next, decreasing lambda d and can further improve design diversity, as shown in the figure below, where the key geometric features are partly kept and their performance has a significant improvement. This example clearly demonstrates that the structural performance is not the only consideration in structural design. Creative ideas to improve aesthetic quality and achieve other design requirements are also valuable considerations. In conclusion, the contributions of this study include: we proposed an interactive topology optimization method considering subjective preferences. The proposed method includes subjective scoring and drawing systems. Using the proposed method, diverse innovative designs can be created while maintaining a high level of structural efficiency. A digital design tool is developed to assist design exploration using multiple optimizers. Design parameters can control final topologies to be performance-driven or preferences-driven. The full paper has been published on computer IDD design. This is a reference list. Finally, I would like to thank distinguished Professor Mike Shea, Dr. Jeff Lee, and Professor Roland Snokes for their supervision. Thanks to Mary for helping me prepare the presentation. Thanks to Dr. Xin Yan, Professor Weixin Huang, and everyone in CSM for the advice and support. Thank you for your attention.
Thank you, Albert. It was an amazing lecture and very inspiring. I especially like the iBESO software part because it reminds me somehow about Midjourney and generate like for different images for different kind of methods, but with the same or with the similar structural performance. And I have like two questions about the iBESO software. One is that because you're actually drawing the solution, you make a drawing first or upload the image, and then you generate the results. So I would like to ask, first thing is that can you upscale the results? For example, right now you currently have the radius or like the scale to change it, and can you upscale it to a bigger image or bigger plan? And second question is that right now I see all the thing is like the analytical result is done in 2D. Is there a way or is there a potential to make it from 2D results go into 3D structural analytic results? Thanks.
Okay. Okay, thank you for your question. Amazing question. The first, I will answer the first question. Firstly, I haven't implemented the upscale function in iBESO. This is because I just I think it is not a very complex function. This is the publication stage. I just published a paper and software. I haven't considered too much about user interaction and some commercial applications. But from the principle, that is very easy because you can just apply to change the texture with different resolution or something. You can apply using the different texture. You can create different solutions, I guess. And for the second question, for the 3D, there are a lot of challenges. For example, you can't drawing on space. Yeah, this is a great challenges. So this is why drawing system haven't been considered to extending to 3D cases, but scoring it is possible. I think in my future research, I will develop the 3D version because our reality is 3D, our world is 3D. We need to design 3D structures. I think maybe next year you will see the result. Thanks. Thank you for your question.
I'm looking forward to it. Thank you for your answer. Any more questions?